Hi, Math 30-1s, and welcome to our first video lesson as we try to remote learn from home. This is, I think, take 9 for me. The last one got interrupted by announcements, so trying this again. It's obviously new for me, and it's kind of awkward and feels very weird teaching to a computer versus teaching to all of you sitting in your desks. So, bear with me, it's going to be a little different, and we're just going to do the best we can and hopefully learn some math. So, as you know, we are moving into chapter 9 on rational functions. That's why I had you last week do some review of rational expressions, particularly being able to simplify a rational expression and go over what the non-permissible values are. So those are two of the really big skills that are important as we move forward here. And so I've got my notes set up, the same notes I've shared with you. I hope you've got your TI-83 calculators because we're going to do some graphing today. And let's go and see what we're doing. So we're going to do just 9.1 this week, which is that we're going to take a look at rational functions using transformations. So we're going to use all of the things that we have learned already about transformations and apply them to rational functions, just like we did with polynomial functions and like we did with square root functions and like we did for just generic functions when we first learned about transformations. So the two main things we want to get at it today are the ability to graph and analyze a rational function and to take a look at what the end behavior of that function is when we get close to the non-permissible values. Okay, so to start us off, just definition of a rational function is that it is a function written in the form of a fraction, where both the numerator and the denominator are polynomials. So there's our mathematical definition, f of x is equal to p of x divided by q of x, where both p of x and q of x are polynomials. So recall from our unit on polynomials, that means that the expression can be constant, just a number by itself, or it can be the sum of terms that include coefficients and variables as long as the degree on the variables is positive and a whole number. That's what a polynomial is. And of course, we see that same restriction that the denominator, so q of x, cannot equal 0. Because again, you cannot divide by 0. It makes no sense. Logically, I can't have 20 things and divide them into no groups. Okay? So that's our non-permissible value. Whatever the value of x would be that would make the denominator equal to 0 is something that x, in fact, cannot be. Okay. So we are going to, of course, first look at a base rational function, so the simplest rational function is 1 over x. And I've already given you the graph here. And as you can see, we're going to talk about domain range and then the equation of the vertical asymptote and the horizontal asymptote. So obviously you need to talk about what asymptotes are because I don't think we covered that very well or at all actually in 20-1, those of you I taught 20-1 to last year. Or not very well. So we're going to go over that again. However, what I want to do first is slightly move away from the notes here for a second and talk about or show you why 1 over x looks like this when we graph it. Okay, and then we'll come back to this and go over those things. So I'm just going to switch screens here for a second, Anya. And I'm going to change our note. So here I've got the function. So f of x is equal to 1 over x. And a really important thing if you're not in the habit yet of doing, hopefully you can start developing this habit, is always think first about what your non-permissible value would be. So obviously for this function, it's that x cannot equal 0. Right? I would get an undefined function or an undefined fraction, which means it's impossible to graph. Right? There is no value for y when x is equal to 0. Okay, so I've got two table of values set up here because I want to take a look at the negatives as well as the positives. Okay, so we'll start off with the positives just because that tends to be our habit. Right, so start off with if x was 1, well, 1 over 1 then would give us a y of 1. That's easy enough. If x is 2, well then y is equal to 1/2, 1 over x. If x is 3, then y is equal to a third. That's a little messy, sorry. There we go. And of course, if x was 4, then y would equal a quarter. So as we can see, as the value of x gets bigger, y is getting smaller and smaller. However, are we ever going to get so small that we hit 0? And the answer to that is no. There is no way to get to 0 for y when x cannot equal 0, right? So if x was 10, well, y would be a tenth, so small, but still a number. If x was 100, y would be 1/100th, getting close to 0, but we're never going to hit 0, okay? Now, you might have noticed that I started this table of value with x as 1 kind of in the middle, and the reason for that is because I want to approach 0 now on the positive side, but of course I can't actually get to x as 0. So what if x is a half? Okay, then if I substitute that into the function 1 over x, I would have 1 divided by 1/2. Well, dividing by a fraction is the same as multiplying it by its reciprocal. Reciprocal of 1/2 is 2. So my y value would be 2, because I would get 1 times 2. If x was a quarter, again, I'd be multiplying 1 by the reciprocal of a quarter, which is a 4. So y would be a fourth. If x was 1/10, y would be 10. So the smaller my x value gets, or the closer to 0 the x value gets, the larger the y value will be. So that's where we see this graphically, right? So we start off with x was 1, then y was 1. So we start off right there. And then as our x values increased, our y values got smaller and smaller and smaller. But again, they are never going to hit 0. That was weird. Not quite sure why it translated into a straight line right there. Right, so as our x values increase, our y values are going to get smaller and smaller. As our x, though, approaches 0, our y values get larger and larger and larger. But again, they are never going to cross the y-axis because we can never get x to equal 0. So the smaller the x value gets, the larger the y gets. That's where we get this shape from. And of course, we're going to see the same thing on the negative side, right? So if we had x was -1, okay, well then y would be -1. If x was -2, well then y would be -1/2. If x was -3, then y would be -1/3, and so on, right? So the larger the absolute value of x is, the smaller the value of y is. The smaller the absolute value of x, so if I did -1/2, then y would be -2. If I did -1/3, y would be -3, and so on. So we're going to see the exact same pattern we saw with the positives, only obviously now with negatives. And so, same thing, right? When x was -1, y was -1, right? Right down here. And then we saw as x got smaller in value, or the absolute value of x got larger, our y values got smaller and smaller and smaller. But we are never going to get to a y value of 0. So we are never going to cross the y-axis. And as we started to use fractions for our x value, we started to get larger and larger values of x. But again, we can never actually, larger and larger values of y. But of course, we're never going to cross the y-axis because our x is never going to be 0. That's our non-permissible value. So that's why we end up with this particular unique graph. This is the graph of a basic rational function. Okay, so hopefully that makes a little bit more sense now. So we are going to then take a look at domain and range. Okay, well, domain, we're seeing that x can be pretty much any value except for it cannot equal 0, cannot equal the non-permissible value. So that's our domain. Quite simple. Right? So our domain is x such that x cannot equal 0, but x is any other real number. Okay? So domain is your non-permissible value, your NPV. Okay? No, that's very messy, sorry. There we go, let's try again. Range. Well, let's take a look at the values that we see for y. Well, we were seeing that y could be any value except for, we talked about how we were never going to cross the x-axis. So y was never going to be 0. All right, well, that's our range then. Y such that y is never going to equal 0, but y can be any real number. Okay, now this leads us to our asymptotes. So an asymptote is something that, or is a point, or in this case a line, that x and y both can approach, but they will never cross. They will never actually get to that value. So we see for x values, so our vertical asymptote is here. We are getting closer and closer and closer to this line of x is equal to 0, but we're never going to get there. We're never going to cross it. So that leads us to our our vertical asymptote. The equation of our vertical asymptote is x is equal to 0. So it is related to your domain. And then we see a similar thing, obviously, with our horizontal asymptote. Right? We're getting closer and closer and closer to x being 0, being y being 0, but we are never going to cross the y-axis. We're never going to get there. So that's our asymptote. This value of y that we are going to get very close to, but never cross. And so that will lead us to our equation for asymptote, which is that y, or the equation of our horizontal asymptote, is that y is equal to 0. Again, then, related to the range. Okay? So hopefully that makes sense. So let's move on. We then are now going to look at transformations. So which transformations, here's a question first, which transformations would change the domain and range of this function? What could you do to this function that would change its domain and range? Think about that for a second. Okay, so if you reflected it, would that change domain and range? Well, no, we would still have the same, right? We would just have, if we reflected it, we would just be in opposite quadrants, right? We'd be like this. So reflection won't do it. If I stretch the function, well, that's not going to change anything either, right? If I vertically stretch it, and horizontally stretch, I can horizontally stretch, I guess, to a degree too, although it doesn't actually change much, and we'll see that. We focus more on vertical stretches here. Horizontal stretches don't actually kind of work here. But I still can never cross the axes, even if I stretch, right? Because my non-permissible value is still that x cannot equal 0. So the only transformation that we could apply to this that will change our domain and range is if we translate it. If we move the entire function up or down or left or right. Okay? So, which transformations would change the value of the domain and range? Translations. So, here we see our basic, generic, I guess, rational expression, rational function with transformations. Okay, so we see similar, or we see the same variables that we've been seeing for transformations this whole time. So what's our a value again? Well, a is our vertical stretch. Sorry, still getting used to writing with the stylus. I'm actually doing this on my iPad using an app. So I just got my stylus the other day, so it's a little different. So this is our vertical stretch. Maybe I'll just write them over here. So A is our vertical stretch. Okay, and it's of course by a factor of A. Just getting a message on my computer that my battery's getting low, so just gotta plug it back in. Okay, so A is our vertical stretch by a factor of A. H, as always, is our horizontal translation. And K, oh, this is really messy, sorry guys. Let's try this again. So K is our vertical translation. And H is our horizontal translation. Okay, sorry. Again, getting used to technology here. All right, so let's take a look at some examples. So determine some characteristics of the following graphs. So we want to take a look at what the equations look like, and then how that relates to things like our domain, our range, our non-permissible values, and our asymptotes. Okay, so here we can see in this first one, y is equal to 6 over x minus 3 plus 1. So we've got a vertical stretch here of 6, right? Our a value is our numerator. We are translating horizontally by 3 units. And remember, when it's x minus 3, that means our h value is actually positive 3. So we are going to move 3 to the right. And our k value is plus 1, so we're going to move up 1. So let's just take a quick look at what that actually looks like. So I'm actually going to bring up my calculator here. I'm just going to move some stuff around so hopefully we can try to see all of this in one screen. All right, so I'm going to go into my calculator here, and we're going to do y is equal to 6 divided by, now you do want to put your denominator in brackets, you guys, remember, because you got to tell your calculator the order of operations you wanted it to do. So we want the entire x minus 3 to be our denominator, so I'm going to put that in brackets. X minus 3 bracket plus 1. Now I'm going to graph it. And sorry, my window settings for some reason are not typical, so there we go. All right, so there we see our graph. Okay. So what is our non-permissible value? Well, of course, our non-permissible value we get from the denominator of the expression. So x cannot equal 3. And what's our domain? Well, let's take a look at that. Our domain is that our graphs are approaching, and I can let's change our window settings maybe a little bit here. Let's go maybe smaller. Let's go -20. So, oh, what did it not like about that? Maybe I need to actually put it in with the calculator and not type it in. Sorry, guys. So -20 to +20, and let's go up by 2's. And we'll do the same for our y's. Let's go from -20 to +20, going up by 2's, and let's regraph that. All right, so as you can see, we're getting closer and closer maybe going up by 3's, or sorry, going up by 2's misses what we actually makes our going to go up by 1's here. Sorry, guys, because I want to actually see the third tick. All right, so there we go. Now we can see it better. That this line, this part of the graph, is going to approach x is equal to 3, but we're never going to get there. So our domain is again related to our non-permissible value. So our domain is that x cannot equal 3. Other than that, it can be any real value. And what's our range? Well, if we take a look at our graph, here we actually do cross the x-axis this time. All right, we are above the x-axis. And if we go into our table of values, you can see that. Right, so here's the error when x is 3. So that's our non-permissible value. That's what it'll look like if you looked in your table of values. And so as we can see, as our x values get larger and larger and larger, we are getting smaller and smaller and smaller values. All right, so when x is 10, we're at 1.8. And then when x is 20, we're 1.3. Right? We're getting smaller and smaller, but what are we never going to cross? We're never going to hit 1. And I can scroll back up into the negatives and we'll see a really similar picture, right? We're actually going to see the exact same values, only negatives, right? So, or similar values, right? So I'm getting closer and closer here to 1, right? 0.8, 0.9, but I'm never going to hit 1. So our range is that y cannot equal 1. Okay, but of course, it can be any other real number. Okay, so what's the equation of the vertical asymptote? Well, your vertical asymptote is related to your range, right? If I go back, related to your domain. I'm sorry, I said that wrong, right? So there's our graphs again. So our vertical asymptote would be this line here. What vertical line are we never crossing? We are never crossing x equals 3. So again, related to your non-permissible value and to your domain. What's the equation of our horizontal asymptote? What horizontal line are we never crossing? Well, that's related to your range. You are never going to cross, you are never going to get to y is equal to 1. Okay, so we see these exact same values in the equation, right? So our domain is related to our horizontal translation, moving left or right. Right? It's also, that's what makes our non-permissible value. So our non-permissible value, our domain, and our equation of our vertical asymptote are all related to the h value. So let's just highlight that, I guess. Right? So our asymptote, our vertical asymptote, our domain, and our non-permissible value are all related to the h value. And the k value then is related to our range and to the equation of our horizontal asymptote. Okay? And in terms of mapping, right, if we use ideas of mapping from our previous transformations, well, what's our mapping? So x and y, well, your stretch value is 6, right? Remember, this is our vertical stretch value, so it's what we multiply the y by. So we're going to multiply 6 times the y, and we're going to add the the vertical translation to it. So we're going to add 1 to it. Whereas x is only going to be affected by the horizontal translation, so x plus 3. Right? And if we take a look here at the graph, that's what we see, right? Or better yet, let's take a look at our table of values. Right? So if I take the point that would have been on the original, 1, 1, and just for the sake of this, let's graph the basic rational function 1 over x. Oh, I didn't want to actually change what I was doing. Sorry, guys. So 6 divided by bracket there. I want to graph a separate one. 1 divided by x. So there's our transformed one, and the red one's our original. So this point 1, 1 is going to shift in 3 different ways, right? It's going to be horizontally moved over 3. It's going to be moved up 1, and then it's going to be stretched by 6. So it's going to be multiplied by 6. And so if we look at that in the table of values, sorry, I got to scroll all the way back up. Actually, let's just hit no, I thought I could just do a shortcut, but apparently not. All right, almost there. Okay. So so x is 1, y is 1. Well, we're going to shift, according to our translations, we're going to shift our x over 3. So x would become positive 4. And so we see that. So now if we take a look at when x is 4, what's our value? Well, our value is 7, which is equal to 6 times 1 plus 7. So the point 1, 1 is going to be transformed into 4, 7. We're going to move it over to the right 3. We're going to move it up 1, and then we're also stretching it, timesing it by 6. Right? So that's where we get that transformation from. Okay. If we take a look at this next one, right? Let's first do the let's first talk about non-permissible value, domain, range, equation of asymptotes and things, and then let's graph this one. Okay, so what's our non-permissible value for this one? It's that x cannot equal negative 2, right? Because negative 2 plus 2 would give us a denominator of 0. Our domain now we know is related to that. So our domain is that x cannot equal negative 2, but x can be any other real number. All right, what's our, so we also know that that's related to our equation of our vertical asymptote. So x is equal to negative 2 is the vertical line that our graph is never ever going to touch. We're going to get close to it, but we're never going to reach there. Okay? Now what's our range related to? our range is related to our vertical translation. So we are never going to actually hit 7. And we're going to see that when we graph that. But y can be any other real number. And so that's going to be our horizontal asymptote is y is equal to 7, because we're going to shift that base function up 7. So basically we're going to take that initial horizontal asymptote, right? So if I just scroll back up here, so we're going to take this initial horizontal asymptote, which is 0, so this line, and we're moving it up 7 spots, so up to 7, right? That's essentially what we're doing. Right, and so of course our mapping then, just to finish off our note, our mapping is that our xy is going to become x minus 2, because we're moving to the left 2. We are going to stretch the y values by a factor of 4. So 4 times y. And we're going to add 7 to it. And that would be our mapping. So again, let's take a look at what that looks like on the graph. So using our graphing calculator, I'm going to get rid of this function, and we're going to do this time 4 divided by x plus 2. Again, I want my denominator in brackets. And add 7 to that. All right, so there we see. So the red is our original line. I'm going to change my window settings back just to normal. All right, so there we can see how the horizontal asymptote has been moved up to 7. 1, 2, 3, 4, 5, 6, 7. There we are. So we're never crossing this line. Again, we can go into the table of values and check that. Right? So as our x values increase, our y's are going to get smaller and smaller, but we're at 7.2, 7.1. We're never going to hit 7. And on the negative side, right, by the way, of course, you're seeing your non-permissible value there at -2. And on the negative side, we're going to get close to 7, so 6.7, 6.8, but we're never going to hit 7. So that's our horizontal asymptote, also related to our range. So we moved up 7. We've also moved to the right 2. So you can see that in our vertical asymptote. Instead of being at 0 before, it is now at -2. We've moved to the left 2. Okay, and we've also stretched this. We've stretched it by a factor of 4. So we've taken each x value and timesed it by 4, and then stretched it up 7. Right, so that's why we're seeing kind of a more drastic curve than we did to this one. All right, so that's our kind of basic transformations. So what we're going to take a look now is at a couple example questions. Okay, so first off, what is the domain and range and location of the vertical asymptote just for your basic general function? So helpful to know. So your domain, as we've been saying, is related to your h value, which is also related to your non-permissible value. So your domain is x such that x does not equal h, but x is an element of the real number system, so all of the real numbers are good. Your range is related to your k value. So y such that y cannot equal k, but y is an element of the real numbers. Okay? So h and k then are related to your domain and range, and as we've already talked about, they're also then related to your vertical and horizontal asymptotes. So your vertical asymptote is that x is equal to h. Your horizontal asymptote, I know the question didn't ask it, but we might as well write it, is that y is equal to k. And there's your generic kind of what we can use then all the time moving forward. All right, what if a is negative? How is that going to change? So a being negative, of course, would give us a reflection across the x-axis, just like a being negative has always done. So your domain and range will not change. So domain and range will stay the same. However, your actually nothing's going to change. Sorry, all of them are going to stay the same. So domain, range, and vertical and horizontal asymptotes will all stay the same. Let's change that. All will stay the same. So all characteristics will be the same. However, you will have a reflection can't spell reflection today. Across the x-axis. So make a rough sketch of y is equal to a over x minus h plus k if a is greater than 1. So if you actually have a stretch factor. If h is greater than 0 and k is positive, should have just said then k is also greater than 0. Okay, so let's say we're going to do this for, so let's just make up 1. Let's do an a of 2, an h of 1, and a k of 3, just to make sure we've got all the different numbers being different. So our first, how I always approach these is that I think of the base function, right? So 1 over x. So remember, when we've got 1 over x, when x is 1, your y is 1. When x is 2, y would be a half, and then a third, right? You're going to get really close to 0. And conversely, when x is a half, you're going to be at 2. And then when x is a third, you're going to be at 3, and you're going to get really close that way, right? So what I'm going to do is then I'm going to take that first value and I'm going to move it. So one way of doing, that first value, I'm going to take the point 1, 1, and I'm going to move it. The other way you can do that is kind of envision moving your asymptotes first and then doing your stretch to it, right? So right now, and of course, my base function would be the same in the negative side. I'd be at negative 1, 1, and then like that, right? Sorry, again, still trying to get used to that stylus. Okay. So that's it, got vertical and horizontal asymptotes of 0 and 0. But if my h is 1, that means we're going to shift over to the right by 1. So I'd have a vertical asymptote now at 1. And we're also moving up 3. So I'm going to have a horizontal asymptote at, I'm drawing that at 4, and I should be drawing that at 3. So, right, that's where our asymptotes are going to be. So if I was drawing this function normally, just the base function with these translations, my first point would be 1 over and 1 up from the cross of the asymptote. So you can almost envision where the two asymptotes cross as being like your origin. But now we're stretching by a factor of 2. So instead of being over 1 and up 1, I'm actually going to multiply by 2. I'm going to stretch it up. So I'm going to be 1 over and 2 up from the cross of the asymptotes. All right, so I'm actually going to be there. And instead of being over 2 and up a half, I'm going to be over 2 and up 1 from the crossing of the asymptotes. Right? So I'm going to actually be there. And when I'm over 4, I'm going to be up a half. So my line would be like this now instead. Right? And then conversely, when I'm over only a half, instead of being up 2, I'm going to actually be up 4 from the crossing of the asymptotes. So that's where we get the stretch from. Again, of course, you can do that as a mapping notation, right? So our mapping notation would be that x to x we're going to add 1, and to y we're going to multiply by 2 and add 3. So the point 1, 1 would become the point 2, because 1 plus 1 is 2, and 2 times 1 plus 3 is 5. So that's what I had. I had 2. I had a point at 2 and 5, that point right there. Right. So you can either view it that way, as I said, kind of just move your asymptotes and then graph according to the pattern, or use your mapping notation. Okay? All right. Got a couple other examples here for you. Oh, sorry, I guess I only did half the function. Where you're just going to have the mirror image on the diagonal quadrant, right? So instead of being over 1 to the left and down 1, I'm now going to be over 1 and down 2. So I'd actually have a point here at 0, 1. And then instead of being over 2 and down a half, I'm going to be over 2 and down 1. So I would be here at negative 1 and 2. And I'd have to go over 4 to be down a half. Right? And conversely, if I'm only over a half from the crossing of the asymptotes, I would actually be down 4 from the crossing of the asymptotes. So I'd be here. Again, the other way of doing that is using your mapping notations. And sorry, I'm getting still issues with the stylus. So anyway, something like that. All right. So now we're being asked to write the equation for each function in that form. So as you can see, what I've added to the picture is the dotted lines for the asymptotes, because those give you your h and k right off the bat. Right? So as we can see, if our vertical asymptote is here at 1, and our horizontal asymptote is here at negative 6, because we're going down by 2's on the y-axis there, right? Well, that gives us our h and k values. So we've moved over 1, so our h is 1, so x minus 1, and we've moved down 6, so we're minusing 6 from the entire rational expression. So now what you have to do is figure out your stretch. So how do you do that? You take a look at whether you are over 1 and up 1. Now, the one thing we should already see is that we've got things in the different quadrants now almost. So again, if you kind of view where your asymptotes are as like moving your entire quadrant system, we are now in quadrants 2 and 4 versus 1 and 3. So that means your stretch value is actually a negative. This has been reflected. All right? And so what I look for then is the base pattern of 1, 1. So over 1, in this case, down 1, if our stretch factor was a 1, I would expect to see a point there. At 2, oh, sorry. And I've also got to remember that we're not even going over the y values. You're going up by 2's, not by 1's, right? So if I was expecting a stretch, or if I was looking for a stretch value of 1, I would be over 1 and down 1. So I'd be somewhere about there if I had a stretch value of 1. But I don't. How far are we over? We're over 1 and down 4. So that makes our stretch value a 4. And again, it's a negative because we have flipped across the x-axis. Okay? So that would be the equation of that rational function. And I've got a second example there for you. What is the equation of this function? Right? So a different approach to doing this, okay, is to think about your mapping. Okay, so the base function will always have a point 1, 1, right? Over 1, up 1, because if x is 1, then y is 1 over 1, which is 1. So then you could take a look at where that equivalent point is on your new graph. So that point is here at -2 and 1. Okay, so we have not we've not actually been stretched here because our y value is still the same. We have just been translated over horizontally, right? So what that means is we've gone over 3, right? We've had to minus 3 from our x value. So that gives us our h. So our h is minus 3, so we'd have x plus 3 then. We haven't moved up or down, so we don't have a k value, and we haven't been stretched. So our numerator is a 1. So that is our function, 1 over x plus 3. Okay. So that is it for your notes. I hope that helps. Your assignment has been posted, and as I said, I'm actually going to take you through some of the, if you want to watch, I'm going to take you through some of the example questions from your workbook as well. Okay? See you soon, guys.